In this lesson, which is part 2 of buffers, we will examine the effectiveness of a buffer, so how well it works when strong acid or strong base is added to the system. We'll look at the buffer capacity, and we'll also look at how to prepare a buffer, which will include how to choose the appropriate substances to make a buffer of a particular pH, as well as what is the ideal ratio of acid and base in the system. To look at the effectiveness of a buffer, we want to look at the effect of adding strong base or strong acid to the buffer system. The system that we're going to study is one from a previous example where we had acetic acid and the concentration of the acetic acid in our buffer was 0.09 and the concentration of the acetate ions or the A- was 0.11. We calculated the pH of this buffer previously and it was 4.83. Now what we're going to do here is look at the effect of adding 0.01 moles of strong base to this buffer. And we want to look at the new pH so that we can see how effective the buffer was, remembering that the goal of the buffer is to keep the pH of the system relatively constant. The key here is to recognize that when you add a strong base or a strong acid, this is going to be a complete forward reaction. We're going to organize our data similar to how we do for equilibrium, but instead of it being initial, change, and equilibrium, it's going to be initial, change, and final because this is a complete reaction. So in our buffer example, the concentration of the HA is 0.09, and we are adding 0.01 moles. It's a 1 liter solution, so the concentration of that hydroxide in the mixture is 0.01. And we've got a concentration of A minus, or the acetate ion, of 0.11. Okay. The water is nothing for us to worry about. Now, in this case, the hydroxide is the limiting reactant, and this is a complete reaction, so it goes to 0 as we complete the reaction. So the changes, like before, are in terms of x and consistent with the stoichiometry. So for HA, the final concentration, once this particular reaction is complete, is 0.08, because we know that the x value is 0.01. The concentration of the A minus, because it increases by 0.01, is 0.12. Now we want the pH of the solution, and if we recognize that we still have a buffer because we've got our conjugate acid-base pair, we're able to use the Henderson-Hasselbalch equation in order to calculate the pH. It is the negative log of the Ka, which for acetic acid is 1.8 times 10 to the negative 5, plus the log of the concentration of the base, which is 0.12, over the concentration of the acid, which is 0.08. If we calculate the pH, we get 4.92. So what we can see is that by adding 0.01 moles of base, the pH changes from 4.83 to 4.92, which is a very small change in pH relative to what the change would be if we added that amount of base to pure water. If we added that amount of base to pure water, the concentration of the hydroxide in that solution would be 0.01, which would give us a pOH of 2 and a pH of 12. So in pure water, adding that amount of hydroxide would cause the pH jump from 7 to 12, which is a difference of 5 pH units. By adding it to a buffer, the buffer is able to counteract the effect of the base and basically consume it, which limits the change in the pH. So this here is a diagram, a visual representation of that. So if in this case we're adding acid, if you started at 7, if you added acid to pure water, the pH would drop quickly and significantly. But if you add it to a buffer solution, it remains relatively constant. Okay, so in this next example, we've got a buffered solution of NH3 and NH4Cl. So our pair is the NH3 and the NH4Cl. This is a base buffer, so we expect it to have a pH greater than 7. Now I prefer to always use the pH formula with the Henderson-Hasselbalch. But in this case, if you want, you could use the pOH formula. Okay, I'll show you using the pH formula, which is the pKa plus the log of concentration of B over concentration of A. Now, what needs to happen here is you need to convert the Kb and find the Ka. Okay, and you need to be careful because the NH3 here is the base and the NH4 plus is the acid in this pair. So the Ka that we need to use is 5.56 times 10 to the negative 10, which we found from Ka times Kb is equal to Kw. Okay, so what you find the pHs here is 9.05. When you have a buffer that's prepared using a basic solution and its conjugate, you expect the pH to be greater than 7, okay, which it is. In part B, we are asked to calculate the pH of the solution that results when 0.1 mole of gaseous HCl is added to 1 liter of the buffer. So what we need to do here is look at what reaction will happen with the HCl. The Cl is a spectator ion, so what we're actually adding is H plus to the system. When you add acid, the complete reaction that you're going to use is the reaction of the base with the acid. So I'm adding H plus to NH3, which leaves me with NH4 plus. Anytime you are adding a strong acid to the system, we're going to use an ICF table because this reaction goes to completion. So the initial concentration here is 0.25 for NH3 and 0.40 for NH4. We've added to the system 0.1 mole per liter. And that's going to go down by X, and because it's a strong acid and this reaction goes to completion, the H plus, being the limiting reactant, goes to 0. So now we look at what we have in the system. We've got a buffer of NH3 and NH4 plus, so we can use the Henderson-Hasselbalch equation to calculate the pH. So negative log 5.56 times 10 to the negative 10 plus the log of 0.15, which is the base, over the acid. And the pH drops, which we would expect because we added acid, but it does not drop significantly. Now, with the examples that we've shown to this point, have involved adding quantities to a liter of solution. And so no dilution has been required. The examples that we're going to look at in class are going to require some initial calculations that you'll want to look out for. Okay, if you mix two solutions together, you're going to need to dilute them appropriately using C1V1 equals C2V2 in order to determine the concentrations initially of the solutions. Now, when we talk about buffer capacity, we're talking about how much hydroxide or hydrogen ions a particular buffer can form, can absorb. And we're going to look at an example here to compare two buffers of acetic acid and acetate. And we're going to have one where we start with 5 mole per liter and another one where we start with 0.05 mole per liter of each of the solutions. Now, in each case, the starting pH, because the acid and the base are in equal concentrations, are both equal to pKa. And remember that this comes from the fact that the log of 1 is 0. If we study solution A, okay, we're adding acid to it, so we want to look at the reaction of the acetate ion with the hydrogen ion that's been added. It's a complete reaction, so we've got ICF. I'm starting with 5 of each of these, and I'm adding 0.01 moles of this. So when I look at the changes, again, this goes to 0. This will change to 4.99, and this will change to 5.01. When you calculate the pH of this new solution using the Henderson-Hasselbalch equation, which I would encourage you to stop and do, you'll see that the pH only changed by 0.01. Let's compare that to a solution where the initial concentrations are 0.05. Okay. If you set up the same ICF chart, okay, in the space below solution B, which I would encourage you to pause the video and do right now, what you will find is that the final concentration of the acetic acid is 0.060, and the final concentration of sodium acetate, more importantly the acetate ion, is 0.040. Next, use the Henderson-Hasselbalch equation to calculate the pH, and what you find is that the new pH of this buffer solution is 4.92. So the change in the pH in this case is 0.19. Now, solution B still has a small change in pH because it is a buffer, but what you can see from this is that the larger the concentrations of the acid and the base used to prepare the buffer, the more it's able to resist changes in pH. So solution A in this case has a higher buffering capacity than solution B. It's able to consume a greater amount of H+ without changing the pH. Now, when we want to prepare a buffer, there's usually going to be, or there's always going to be, a pH that we want for our buffer. And there are two components to consider here. When we look at the Henderson-Hasselbalch equation, which is pH is equal to pKa plus the log of the anion over the acid concentration, there are two factors that go into controlling what the pH of a particular buffer will be. So the first component is the Ka of the acid that we are dealing with in our buffer. And as well, there is the ratio of the anion and acid concentrations. Now, when we look at a buffer, the ideal ratio is 1 to 1. So we're going to use that fact, and when we have a particular pH that we want to achieve, we're going to use the pKa in order to select an appropriate substance. So let's look at an example here. A chemist needs a solution buffered at 4.3, and we can choose from the following acids and their salts. So we would have chloroacetic acid and then the salt of chloroacetic acid, propanoic acid and the salt of it. If we want a pH of 4.3, the substance that's going to help us to achieve that is the one with a pKa that is closest to 4.3. So what we want to do is find the pKa for each of the solutions. In this case is 2.86, 4.89, 4.19, and 7.46. Now, one thing to point out here is that really you could estimate these pretty well. Okay? So when you're looking at logarithms, this is 10 to the minus 3, okay? So that you know that the pK is going to be somewhere around 3. In this case, it's 10 to the minus 5, okay? So it's going to be around 5. The higher this number, okay, the smaller the value, so therefore the closer it is to 4, because this is bigger and bigger and bigger. This one's bigger than this, so it's going to be closer to 4. Okay, so in terms of which one of these is closer to 4, it's going to be the one with the larger coefficient. Okay, this one here, 10 to the minus 8, okay, slightly less than that at 7.46. Okay, so you can estimate these. So in this case, the best one is the one with the pKa that's closest to 4.3, okay, which in this case is the benzoic acid. Now, another thing to point out here is that the ideal range for a particular buffer is plus or minus 1 of the pKa. So for benzoic acid, it can work as a buffer of a pH from 3.19 to 5.19. So that's how you can decide what the ability of a particular buffer is. Now in the second question here, it asks you to calculate the ratio required to yield this pH. So what you are going to do is use the Henderson-Hasselbalch equation. So you have a pH of 4.3 that you're trying to achieve. Your pKa for your selected buffer is 4.19. And you've got plus the log of A minus over HA. So we're solving for the ratio A minus over HA. We do that by moving this to the other side and then doing 10 to the power of. Okay, so take a moment, okay, make sure you're comfortable with this calculation. And you should get a ratio of 1.3. So those are the two key components, the ratio of the acid and the base and the appropriate pKa. Okay, so let's look at a couple more examples. A solution buffered at 5 is needed for a chemistry experiment. We're asked if the acetic acid, sodium acetate mixture is appropriate, and then we're asked to determine the ratio. So for this, the pKa of acetic acid is 4.74, which means that the range that's possible for this is 3.7 to 5.7. Okay, so this can be used for this particular buffer. To figure out the ratio, we sub into the Henderson-Hasselbalch. So we've got a pH of 5.0, we've got a pKa of 4.74 plus log of A minus over HA. When we solve for this, we see that A minus over HA is equal to 1.82. Okay, in this last example, we are trying to prepare a buffer of pH 3.9. We want to know if formic acid and its salt, sodium formate, make a good pair, and as well, what will the ratio of the anion to acid be. So in this case, we need to look up the Ka in the table. The Ka is 1.7 times 10 to the negative 4. The pKa is therefore 3.77. The ideal range for this particular buffer is from 2.7 to 4.7, so preparing a buffer with pH 3.9 is definitely possible. To find the ratio of the acid to the salt, we sub into the Henderson-Hasselbalch equation. And we find that the concentration of A minus over the concentration of HA is equal to 1.35. Now we'll be taking these calculations one step further. Once we know the ratio, we can actually make a decision. We can decide the concentration of one of the substances, use the ratio to determine the concentration of the other one, and we'll actually be able to prepare these buffers.